How'd it go?
It's all right. We had people, so I think it was fun doing papers we kind of voted on. So.
Yassine, can you hear us on Zoom?
Yes, I can hear you.
We can't hear you, but I saw you engaged. Okay, let's get started. Today's seminar speaker is Tomer Yavetz. He graduated from Columbia University with both Katherine Johnston and Lam Bui as his PhD advisors. So some of you might remember Lam from last week's seminar, although Tomer and Lam worked on fuzzy dark matter and not on black holes, as Lam was telling us about. So today, or now, Tomer is an IAS fellow out in Princeton at the IAS. And today he'll tell us about stellar streams and stream family.
Thank you, Sarah. Yes, so thank you for inviting me. Excited to be here back in New York to chat about work that in many ways stems from my from my thesis with Catherine, work that I did a lot with Sarah, here with Adrian Presswayland at CCA, as well as a few other collaborators, notably Chris Hamilton, who's with me at the Institute right now as well. And yes, as you see, the title here is Stream Fanning and Bifurcations, Observing Fundamental Dynamics in Stellar Stream Morphology. I don't really think of myself as a stream person, although the word stream appears twice in the subtitle, in the title and subtitle. What I will be trying mostly to talk about is dynamics and how we see it in streams. But this talk is fundamentally, in my opinion, a dynamics talk, although I guess you guys will be the judge of whether that is true. I'm told that a good way to start a talk is to tell you what I'm going to tell you, so I'm going to tell you what I'm going to tell you right now. Generally, we will be looking at non-spherical potentials and seeing that resonances in those potentials break up the orbital structure. And of course, we're applying this to the galaxy, to the Milky Way in this case. So I'll try to prove and show that these resonances in these non-spherical constructions of the Milky Way, which is a very reasonable assumption to make, create all these resonances and orbit families, and I'll claim that you can use streams to actually see these orbit families, these resonances. I'll try to walk you through exactly how we get to this idea of how we see a resonance in a stellar stream. And finally, I'll argue, and again, you guys will be the judges. I believe that the current Milky Way stream catalog is getting to the point that we can start actually searching for these resonances in actual data. This is very exciting, I think, because it means we can start finding the resonances where they are and therefore constraining the shape of the potential, maybe saying something about what is the overall configuration of our dark matter halo.
What's the S in the upper right plot?
We'll get to all these plots. These plots here? Well, I will show each of these plots as we get there. So I promise we will get there. This is just a preview. Good. Kind of overall picture. We live in a galaxy. That galaxy, we think, is surrounded by a big halo of dark matter that sources most of its potential. As a dynamicist, what I like to do is say, well, if we know the potential, we can figure out what the orbits look like in that potential. This is a typical kind of galactic orbit if you look down at the disk, for example. And if you know what the potential is, you know what the orbits would do. That's a very easy thing for a dynamicist to do. Another very easy thing or a relatively easy thing for a dynamicist to do is to say, if I know what the orbits look like, I can then recreate the potential. Only certain potentials will be able to host an orbit that looks like that. So if I can actually see this orbit, I can say, I know what the potential should be. Of course, that's relatively easy to do in the solar system. We've done that many times in the history of astronomy. I think a great example is the discovery of Neptune. We were looking at the Uranus was discovered some mid 1700s. It took astronomers about half of Uranus's orbit, so something on the order of less than 100 years, to see that that orbit didn't just coincide with the mass distribution of what was known in the solar system, and they predicted, oh, there must be another body out there. They actually figured out exactly where Neptune should be, and they turned their telescopes there, and lo and behold, there is Neptune. So determining the mass distribution from orbits is something that we've done. It's relatively not easy, but it's certainly doable, and you can apply it well in the solar system. The problem with the Milky Way is to actually live for long enough to see half an orbit. None of us are going to do that. What we have is basically a snapshot. We have a single still image of the state of the dynamical evolution of our galaxy, and then we kind of want to say from that, okay, can we deduce what the orbits are to figure out what is the mass distribution of our of the galaxy, of the halo in particular, which is the part that we can't see. So I'll say we're going to determine the distribution from stellar streams instead of orbits, because streams are a great way of figuring out what is the shape of an orbit in a galaxy. A stream is what you get when you throw in a globular cluster, typically, sometimes a dwarf galaxy, into a larger body like a galaxy. That smaller body will slowly be stripped from its stars due to just basic tidal disruption. And what I'm showing here is, if you can see the gray line that's moving around, that's the orbit of the progenitor. You can see how the particles from the stream are slowly kind of spreading along more or less the original progenitor orbit. Not exactly one-to-one on the orbit, but it's very close. So really looking at the distribution of stars that kind of have been tightly stripped off from the globular cluster gives us a pretty good picture of what is the orbit, the underlying orbit on which that globular cluster is.
Where did it come from, this globular cluster?
Good question. These things are falling into the Milky Way all the time. We expect there's a certain kind of volume within around us that we are kind of collecting older bodies from around us that are slowly falling in, dwarf galaxy globular clusters. So it is kind of, these things are sinking, and as they sink, they start losing their stars once they get close enough to the Milky Way's center.
I mean, some of them are probably also just in situ.
Or born in situ. Yes, that's true.
But if it is being born inside the galaxy and simultaneously disrupted, like, what was the initial thing in your plot? Was it really?
Good.
Was it
So,
really?
So I just start with a cluster of particles, and you're right to say the formation here is not very well understood. And did it fall in? Did it form in situ? All these things will change kind of how you evolve these things. The other thing that will matter is it a globular cluster, which is dominated by its stellar component, or is it a dwarf galaxy, which comes with its own contribution of dark matter? So the
But this is a weak point in what you are doing, perhaps.
I will say, I won't call it a weak point, I will call it an additional thing that we need to think about, that generally stream people need to think about as we kind of try to model the potential with, so we look at streams, we learn about the origin of the streams, we learn about the globular cluster which it formed, we also learn about the orbit on which it formed. All these things kind of come together. So is it a weak point, or is it just part of the puzzle, I would say? Is that fair? Yeah.
The other boss.
Yeah, no, I'm not saying that it's not a solved problem by any means. It's certainly part of the challenge here.
Can I ask another question?
Yeah.
So isn't it true that the stream will only track the orbit if you start off with a super, super cold, right? Like everything has to be very collimated.
The colder it is, the closer it will track to the orbit. You can actually figure out based on how cold it is, how closely it will track. The hotter it is, the more it will spread away from the original orbit. But a dwarf galaxy, which is much hotter than a typical globular cluster, will also, we can see something like the Sagittarius dwarf galaxy, for example, is kind of wrapping around, and you kind of see its orbit. Now, that is not exactly its orbit. There is a misalignment, but you can deduce more or less what its orbit is based on the configuration of stars.
That's it. Okay. Yeah, I guess I can talk to you about stars, but like, so for Sagittarius, is it true that it's approximately in orbit? Like, could you run a particle around the?
No. It's in none of these cases is it exactly in orbit. There's always going to be a misalignment. If it were exactly in orbit, you wouldn't actually see a stream. The reason the stream formed is because every particle is in a slightly different orbit. So there is an ingrained misalignment which we recognize, we know about, and we have to calculate into all of this to actually fit it. So actually fitting for that misalignment is one of the main ways that you can actually go and say this stream has to have evolved in this potential. So yes, good, definitely part of the equation here, but a well-studied thing in this part. And on the bottom here, I'm just showing that we actually see these streams. This is PAL 5. Sarah here is an expert on PAL 5, probably one of the world experts on that stream, I would say. But this is just that stream, or one globular cluster stream in observation. And we, to your question, these kind of relatively basic assumptions of starting a cluster with a certain kind of prescription and letting it evolve do a pretty good job of reproducing these things, which is one way of arguing that actually this is at least in the right direction of being solved. Good. We have a lot of these streams, almost 100 in most recent count from a paper by or a package, Python package by Cecilia Mathieu, ranging in different guiding center radii, different eccentricities. So these probe kind of a nice swath of the potential. And you would, naively, when I started in this field, I would say, well, we have so many streams, surely we could just be done with it, constrain the potential, and figure everything out. There's a variety of reasons why it's not that straightforward to just take all these streams, combine them all together, and say, what is the one potential that hosts them all? Among these are statistical challenges that I don't want to get into because I don't understand them that well myself. But a big factor in why we don't do that is because these cell streams don't actually behave perfectly. So to your question earlier, I like to say these cell streams misbehave, and they misbehave for a variety of different reasons. So here's kind of just a few examples from recent literature. This is just over the past, I think, 3-4 years, some kind of prominent papers that have found features, morphological features in these streams that don't just align with a simple picture of a simple particle, a simple cluster of stars kind of evolving more or less on the orbit. So you've got things like bifurcations.
Sorry, this bottom right picture, there is nothing to guide your eye. This is just a true picture.
This is just a true picture, yes.
So they are so pronounced, beautiful.
No, very filtered.
Highly filtered and sorry.
You would not see it by eye.
Filtered in terms of spectral things. Or
in terms of like the eye, sorry, I should let you in.
Yeah, so this is data is the point. It's not like a simulation in this case, but filtered in terms of choosing the right distance at which we're viewing this, the right kinematic information, basically picking away stars that are matching kind of the overall location.
So you did something to spectra or something? Whatever, with spectral data.
Yes.
I mean,
in
we
some
can do it with
cases.
just photometry because you kind of, know the cluster, so you can get the isochrone of the cluster, and then you can step in distance, like in magnitude, and search for what
Photometry
stars.
being colors.
Yeah.
A few filters. Okay.
Yeah. So you don't need spectroscopy. That's yet another good way.
But it's not a
Could I
true
paraphrase
picture.
that it's like you remove the things that aren't in a single plane?
Yeah, so you remove things that aren't at the right distance based on where the cluster is. Yeah. So you can search in
And
color,
so it's-
magnitude,
in that respect,
space.
it's not an image, it's an image with a lot of stuff
With
removed.
a lot of stuff removed, yes. But these, I think it's, well, I mean, you're more the observer than me, but I think these are pretty well located, identified kinematically, chemically. It seems pretty robust. These are well identified memberships. I mean, some of these streams have order tens of stars that we've associated with them, but some of them have like many hundreds, if not thousands. So
Yeah, so GD1 up there, which is the one above, that's kinematically selected because that's Gaia data. So what's really cool there is you can search in kinematic space too, because you know how parts of the streams are moving. So you can search around that and be clever about how you filter away everything in foreground and background.
And this one here specifically is two streams that we thought were two streams, and for various modeling reasons, if you put them together in the right kinematic space, you actually see they belong together, so you can recreate it as one stream with a nice gap here in the middle. So there is certainly some interpretation going on here. There's some understanding kind of what is the motion of these stars? Were they born together? Are they moving together? Are they chemically similar? All these things. But if you take all that, I think relatively reasonable assumptions together, you can put together a pretty nice picture of where these stars are. Sagittarius is certainly a stream that you should be able to see, kind of pick out from the data, because that is dominating that area of the halo anyways. So as long as you're putting some sort of a distance filter there, you should be able to see a dwarf galaxy stream like this one here.
Maybe that was related to my question. Is there a difference in density of the stars part of the stream versus the background stars in the same region typically? Or
It depends. So it depends where. So Sagittarius is evolving in an area of the halo where it is the dominant component of the mass. So certainly there you would see it. If you look at external galaxies, that's sort of those are the streams we'd see around external galaxies. Is a dwarf galaxy or a larger galaxy that's been disrupted around it. Some of these internal ones, certainly as you get kind of closer to the galactic center, especially if they're evolving in the disk, then it absolutely requires pulling out not just spatial information. You have to do kinematics, you have to do chemistry, all that stuff to figure out what star belongs to. It's a range.
So the title about misbehaving means that they had like the offset or the gaps or that.
Exactly. There's all sorts of other stuff. It doesn't just give you the simple picture of stars along orbit. You have you have gaps, you have bifurcations, you have these kind of multiple components. Another thing of multiple components, you have fans, all sorts of different things that kind of move you away from the simple picture of stars along stream. You can therefore figure out the orbit. And some people would say that makes it more complicated. It certainly makes it harder to remodel the original potential because there's so many other things that you have to model correctly to get it right. More maybe a glass half full view is that you learn a lot of other things from this along the way. So you learn about the progenitor properties. If there was a globular cluster, what was its original density? How cold was it? Did it fall in with something else? Is it a globular cluster that fell in with a dwarf galaxy? And therefore you see the dwarf galaxy stream and another stream that's kind of kinematically very close to it. Are there subhalos? Is there any dark matter substructure that's coming in the way and disrupting the stream after it started evolving? So that GD1 picture became famous because there's a gap in it that maybe can be explained through an interaction potentially with a dark matter subhalo. Did other satellites in the Milky Way that we know of perturb it? So we know, for example, that the LMC is falling in. That's pulling streams away from their original orbit. We now know that modeling correctly some of these streams requires some non-axisymmetric contributions like an infalling LMC to kind of pull them to their current track. Interactions with the galactic bar is something that Sarah has worked on before, where if a stream comes close enough to the bar in the middle of our galaxy, that will also change its orbit. So all these things are A, complications to that original picture, but B, something that teach us something new about our galaxy or about the potential, about how that stream has evolved. And yet, what I want to do is bring us back to that original question of how do we learn about the overall shape and structure of our galaxy? Given all these other complications, is there a way to still kind of extract from this something about our galactic matter distribution in a way that kind of does away with all these other complications, or at least finds a way around it? And so I'll try to convince you that we can in the rest of this talk. And I'll do that by saying that not only can we see orbits by looking at streams, we can actually see dynamics, so we can see orbital structure. We do that in the solar system. We can look at the rings of Saturn, for example, or we can look at the asteroid belt. You don't actually need to see these things evolving. Just take a snapshot of it, and I would argue you see dynamics. I actually have to credit David Hogg with this turn of phrase. He's the one who started me on this idea of seeing dynamics. But just a snapshot of Saturn's rings, these under and over densities largely evolved from resonances from the dust or the stuff in the rings with the shape and structure of Saturn or its moons, or even with other planets in its vicinity. And you can study kind of why, or the location of these rings basically tell you things about what is the overall structure of Saturn, where are its moons, how is it in resonance with Neptune, for example, things like that. All these very detailed structures here are hints that you can then trace dynamically back to questions of mass distribution, as always. And so my question is, can we do this in the Milky Way? And a lot of people have told me, no, you can't. I want to go back to kind of the first, or the introduction of what many people in my field call the Bible, or galactic dynamics, by Binney and Tremaine, where in the introduction they claim most disk stars have completed over 40 revolutions, and it is reasonable to assume that the galaxy is now in an approximately steady state. I think there's a lot of people who don't like that sentence nowadays, and there's a lot of good reasons that we don't think. We think the galaxy is in disequilibrium, and you can't do a lot of these kind of assumptions that we make about Saturn, which is in equilibrium because the rings have been orbiting for millions and billions of orbits. And yet, I would argue that some of these resonant effects that I will discuss shortly manifest in less than 40 orbital time periods, and therefore we can actually see them when we look at streams. Good. What do I mean by seeing orbital structure and resonance? Let me talk about a resonance now. thrown that word about a bunch. I'm going to show 3 test particle orbits in an axisymmetric galactic potential. A reasonable choice for galactic potential. We know we have a disk. There must be some deviation from sphericity. So we're going to assume this is an axisymmetric potential sourced by a disk and a halo. And I'm going to plot these orbits in R and Z. So they're just going to kind of trace their orbits in R and Z. And these are 3 orbits with very similar initial conditions, but not quite the same. And you can see that these 3 orbits behave very differently. This orbit on the left is what I would call a typical orbit. Fills this torus in R and Z. If you think about it, kind of, if you revolve this torus around, it fills like a donut. And it explores that entire area. Whereas these 2 orbits don't do that. They explore only some subset of the area that is, quote unquote, allowed to them. And that is because they are trapped at a resonance, specifically at the 1-to-1 resonance, which is the resonance that is characterized by oscillations in the vertical oscillations and the radial oscillations being coupled on a 1-to-1 ratio. You can see these stars do a 1 oscillation up and down at the same time they do 1 oscillation in and out. Now, being at that orbital frequency ratio doesn't necessarily mean anything special, because it just you could for any other combination of frequencies that aren't important, you could deviate from it a little bit and slowly, very slowly explore this full phase space. But in this case, because here we have an axisymmetric potential, the Hamiltonian depends on R and Z. As you're moving in R and Z, you're feeling tugs in both of those coordinates. So actually, this orbit gets trapped around that one thin resonant orbit and never kind of deviates to the opposite oscillation like this. And so you get a subset of orbits that are trapped around this resonance. There's actually an equivalent orbit family that is reversed, flipped the other way. But those orbits never shall they interact or meet unless something external pushes you from one to the other. Good, and I think the important thing to say is there's a sharp transition here. There's one boundary orbit where at one point you will never explore anything beyond this diagonal, and then you kind of pop over and you explore everything. It's a stark transition from resonantly trapped to untrapped. And how do we study this? We can evolve these same orbits. I'm going to draw what we call a surface of section or a Poincaré map, which means that every time that each of these orbits intersects the z=0 line here, moving upwards, I'm plotting a point in this right-hand plot that characterizes their radial location and their radial velocity. And I'm just going to keep doing this for enough time. You can see that these things are forming contours. One reason that surface of section plots are great is because they show you that in this projection, you actually condense down to a one-dimensional manifold in this 2-dimensional space, which means there's another conserved action, basically. This is a regular orbit. It conserves not just energy, angular momentum, it conserves a third action, and that means that it's not chaotic. If it were chaotic, things would be spreading all over the place here. The other thing you might notice is that the kind of this regular orbit is doing this large kind of circle that's contained around a point that corresponds to dr=0, whereas the other 2 orbits that are trapped are stuck there at the very top of the plot. And let me just, now we've filled out this surface of section with a lot more orbits. You can see most of the orbits here are untrapped, but are concentric around the central point. These are all the regular orbits, and you've got this resonantly trapped orbit family up here and another one equivalent to it down there.
In the space filling orbit case, why intuitively is it smaller towards smaller r? Is that because the mass distribution is concentrated there, or is that just the random test particle? If you had a perfectly if there were no kind of deviation on r, then it would just be flat because it gets less dense at No deviation in the potential.
in density or potential, yes. So because it gets less dense at higher potential,
Okay,
it can escape further up, farther away from the disk. Yes, good question. But yeah, I mean, once you know the potential, once you know more or less the characteristics, you can actually figure out what should the contour be for a typical orbit, and most of them will indeed adhere to that, and then some of them you'll see that they don't actually fill out all that space that's allowed.
And was this just an axisymmetric halo, or did you have a disk in it?
This has a disk and an axisymmetric halo.
Okay.
This has a disk that more or less matches the Milky Way's disk, as well as a halo that is squashed to a density parameter ratio of 0.8. So its z-axis is 0.8 compared to its x and y axes,
which I chose because it's a reasonable, seems to be where a lot of the literature is pointing nowadays. But even if you had perfectly spherical halo, this resonance would appear because your disk is giving you that axisymmetry. It would appear in a slightly different place. Good, here's the plot you're asking about. So what we're seeing here is a well-studied problem in dynamics and classical mechanics, is the problem of a resonantly trapped orbit or trajectory. These are typically studied with what we call separatrix plots, where your quantity of interest, the way we think about these, or at least in the plot I showed, is you want to change coordinates into what we call slow action and a slow angle, which describes your motion in the resonance. So here you've got the P action is the slow action, sorry, P parameter is slow action, S is the slow angle, describes kind of your conjugate coordinates in this changed reference frame. And you see there's two classes of orbits.
Wait, I just want to make sure I understand. So can you like explain it for a spherical potential, what they would be?
Yeah, so, well, actions and angles in a spherical potential might be something like your orbital, kind of where you are in azimuth, and kind of your angular momentum, so kind of how far you would be. Your action would be something like your angular momentum, and your location along the orbit would be your angle. In this case, we've done a change of coordinates to mimic kind of what is the behavior around this trapped region here. So your action tells you kind of what is the typical oscillation around this plus in the middle here, and the angle tells you where are you evolving around here. The equivalent to kind of the phase space picture is the action tells you kind of what is your oscillation around the trapped orbit. You can imagine kind of a thin line in the middle here that represents the exactly resonant orbit. That's the plus. And then the blue orbit is kind of puffed up around that. So your slow action basically quantifies how far out are you, and the slow angle quantifies where are you along that motion. Is that helpful? Good. And so the key point here, there are two classes of orbits. There are the orbits that are stuck in the middle here that are moving around this point. These are the resonant orbits or the resonantly trapped orbits. And then there are points on the outside that are untrapped. They're revolving more or less as a typical orbit would, maybe with some deviation away from the exact regular orbit as you get very close to this big black line. The big black line is that boundary that I was talking about, the separatrix, and I finally got to my word. This is the separatrix, which basically defines the transition between trapped and untrapped orbits. So sorry, Glenn, maybe the easiest example to give here is a pendulum, a simple pendulum, a rigid pendulum. You've got these orbits, these are the ones that are trapped. You've got circulating orbits, they're going all the way around. Those are the untrapped ones. And then you've got the very special orbit. Well, you've got one very special orbit, which is just the arm hanging at the very bottom. That's the point here. And then you've got one very special orbit where if you launch the arm with exactly the right energy, it never quite reaches the top. That's the separatrix. Right? And I guess the point is, if you think about that separatrix orbit, if you take a little bit of energy off, you are in the librating regime. If you add a teeny bit more energy, you are in the circulating regime. So even though the potential in the setup is perfectly smooth, there's nothing weird about the potential, there is a sharp discontinuity in orbital space, if you will, between these two orbit families. Okay.
So could you just explain again, so what is the x-axis here?
So this is a pictorial representation. It can be a variety of things. We usually think of these as the slow angle that we transform into, and this would be the slow action. Generally, an orbit has, well, a 3D orbit has 3 actions and 3 angles. If it's a resonantly trapped orbit, you can find a canonical transformation that moves you into a set of 2 fast angles and fast actions, which quantify your general motion, and 1 slow action, which quantifies your specific motion with respect to the resonance itself. And so when you do that, you get this picture of kind of the trapped orbits and the untrapped orbits that circulate around. So this would be the action. Sorry, this is the action, which quantifies how far away are you from the actual resonant point, and this is your angle, the conjugate coordinate. And these are any conjugate coordinates. Good. So what do I mean by, how does this affect streams? So let me paint a picture of what we call separatrix divergence. we know these resonances exist. They must exist in the galaxy because the galaxy is not spherical. There's no way they don't exist. They might move around if the galaxy changes shape, but they must be there. That doesn't mean we can easily see them. A snapshot of a single orbit certainly doesn't help you because it's just there. It doesn't matter if there's this contour here or if the contour is just regular. You're just getting a point on this picture. It doesn't matter. A snapshot of many orbits also doesn't help you because it's not like these contours change around the distribution of stuff. It just means that they're mixing things differently. Maybe if you had chemistry, that would give you some sort of a picture here because things are moving in a way that they shouldn't be distributed. But generally, the distribution overall doesn't change. It doesn't change the energy distribution function, for example, of the galaxy. It doesn't change your kind of ability to do genes analysis on the overall structure of the galaxy. So you can't see it if you just look at a snapshot, even of many, many orbits. However, if you have a snapshot of 2 or more orbits with a shared history that you know started next to each other, that can teach you something very interesting. So for example, if those 2 orbits were both regular orbits, they just continue to evolve together, and they'll slowly spread apart, which in what we call typical phase mixing, because one orbit evolves a little bit faster than the other, and they'll spread around in this, and that's actually how you get a typical stellar stream. But they'll stay more or less, and you can figure out how far away they are from each other at any given point. However, if those 2 orbits started in 2 different orbit families, but next to each other, they'll start evolving together. But then all of a sudden, one of them is going to turn around because it's trapped, whereas the other one will keep going, and all of a sudden, they'll be very far from each other, much further than you would expect if you just took the simple picture of phase mixing and believed it. And so that's where stellar streams come in, but let me give a pendulum approximation for what I'm thinking about in terms of stellar streams. You can imagine a cluster of pendula in my picture of kind of my rigid pendulum, and you can start that cluster with a small spread in energy. Okay, that is actually a really good approximation for what a stream is doing. For many initial conditions, that cluster of pendula will more or less stay together and phase mix as we go. So, So if you look at, for example, the first or the third column here, you start, here's a circulating group of pendula, so they're all going to go around with slightly different energies, and they're going to spread out slowly because the one that's going a little bit faster is going to move away from the one that's going away slower, but they'll spread out at a rate that you can predict. Same for the cluster of pendula that's vibrating, that's oscillating. Whereas the cluster of pendula that is on the separatrix, so it's split into a group that's vibrating and a group that's circulating, will spread apart very, very rapidly. Now, I want to say, a lot of people here say, oh, this is chaos. And I push back and say, this is similar to chaos. This is where chaos normally forms. Chaos forms at these boundaries, but for actual chaos, you need there to be another perturbation. You need there to be a second pendulum in this case, where you get kind of, on the separatrix, you get additional kind of movement and distribution that forces some things to behave sometimes as librating and sometimes as circulating. So any given orbit might move. In this case, there's no chaos. There's just a group of orbits, some of which are circulating, some of which are librating, and they split, they spread out completely, even with no chaos involved, just because of the resonance. Back to our picture here, hopefully you can see kind of where I'm going with streams. The idea of streams is the same thing. You've got a cluster of stars that you're starting somewhere here on this picture. That's your initial globular cluster. If that cluster happens to be on a regime where it's straddling the separatrix so that some of the particles are trapped and some of them are untrapped, you should get something that evolves, that diverges from itself much faster. Therefore, we call it separatrix divergence. And here's a quick example of this. So I'm just taking the top half of this plot here. And what I'm doing is I'm initializing in each pixel a globular cluster or an unbound cluster of stars and letting it evolve. And I'm measuring its density over time. And I'm going to color each pixel by the density. And you can see that these darker contours, darker means less dense, I should say, the darker contours in each of these panels kind of conform to that separatrix, which is to say, the stream that is evolving close to the separatrix is spreading out much faster than any of the other streams. The 3 panels here are just 3 different mass scales. So to Oren's question earlier, they all start with a different kind of amount of coldness, so to speak. So all of these streams are much darker because they're all going to spread out much faster than all of these streams. But even in each of these panels, you can still make out the separatrix region because those specific streams are spreading out considerably faster than any of the other ones.
And then in this case, you're not initializing a gravitationally bound clump of stars. right? So that
You
would
can do
change-
it both ways. It makes barely any difference. I've done it both with bound and unbound. I can't honestly remember if this is bound or
Okay.
unbound. The later plots I'll show are all bound.
Okay.
So Sarah's asking, we know the globular cluster initially has its own gravitational well. Does that affect the picture? My answer is not really, because once something is unbound and involving in a stream, the original globular cluster makes very, very little contribution to it. And the way we've proven that is just do both and see that there's very little difference. Good, so let's now actually see what this looks like. What is this actually, so I mean, I've shown the overall density plot, but let's actually see what a stream that is evolving via the separatrix does. So we're just going to evolve the stream. I've got a little time counter up here if you want to see kind of reasonable galactic timescales. The stream is evolving kind of more or less to the solar radius. You can see so far it's doing what a typical stream would do. It's more or less tracking the orbit. To those who were asking earlier, is it exactly tracking the orbit? You can see it's not exactly tracking the orbit. It's close. So far, a giga-year and a half in, looks like a typical stream. Nothing interesting. Let it keep going. You might notice the ends are starting to get a little frayed. You might start picking up there's a red component that's just evolving on the wrong side of the stream. And here we go. There it is. You see that red component being pulled to the completely other side, above the disk versus below the disk. If you keep tracking that, you'll see that red component has now basically formed a secondary stream. It's evolving more or less separately from the whole thing. Sometimes it looks like another component. Sometimes it actually looks like a bifurcation off the original stream. So here we've, through putting a stream next to the separatrix, we've created one of these features that I talked about earlier. It's got very specific characteristics, but we've created one of these features. You also can see at this point already, the blue end is also starting to fan out, doing something weird, but more on that later. And I'd like to highlight this. This happened in a very reasonable galactic timescale for a typical stellar stream. We've not even involved 4 giga-years, and we've pulled off a complete bifurcation.
Was it a randomly chosen initial?
No, I put it exactly where I wanted it, right on the separatrix. Good
So
question.
will it happen?
If it's on the separatrix, I would say
No,
yes.
no. Will it happen in real life?
I will get to that at the very
Okay.
end of the talk. Good question.
Somewhere, can I just ask based on Oren's also orbit question? So you can see at certain parts of the orbit, the stream actually is completely offset from the orbit more times than at others. Can you elaborate on what that means if you happen to observe the stream when it's really not aligned?
You'll usually know it usually happens at pericenter versus apocenter,
Yeah.
just a matter of the kinematics.
So you can model your way out of it, basically?
I believe you should be able to. I'm sure that the people who have thought carefully about stream orbit misalignment have thought carefully about exactly how to model that.
Yeah.
Because the degree of change, it also could be a projection effect, to be honest.
Yeah.
But I think it's a well-solved problem. But I'm not the.
No, I agree. I just
necessarily
wanted to
expert.
elaborate based on Oren's
Yeah,
question.
good. So what do these things tell us? I've said that things will diffuse. I've said that you could form bifurcations. What does this actually mean? What do we learn about the potential when we see one of these things? Besides the fact that, oh, Tomer, you put the stream exactly on the separatrix. That's great, but what does it actually mean in reality? So here I've now initialized a grid of streams, and I know what the potential is, so I know where they are with respect to the resonance. So I can tell you that this top stream is going to be completely resonant. These 3 in the middle will be split between 2 different groups. The second one has most of the stars will still be trapped, but a few will be outside. The separatrix stream is almost 50-50. The mostly non-resonant stream is mostly non-resonant, and then the non-resonant stream, none of the stars are trapped. And we're just going to look at how these evolve and start trying to quantify when you get bifurcations, when you get fans, how much can you actually expect this effect to matter. And so one thing that we note is that you get fans and bifurcations. Not very clear why you get not yet very clear why you get fans and bifurcations in different places. I'll try to explain why. Nor is it necessarily clear immediately why you get this asymmetry where in the first snapshot here, all 3 of the streams get a fan on their trailing arm. And then for some of these streams, that fan more or less disappears, whereas for other it turns into something more like a bifurcation. Some of them also develop a bifurcation on their leading arm. A lot of stuff going on here that maybe my toy picture up until now hasn't well dealt with. And so I want to use the next few slides to try to elucidate exactly why we get these fans, these bifurcations, what we learn from them. Good. In the theoretical picture of this resonance, back to my S&P plot from earlier, you can actually study the quantities of interest in this resonance. So what I'm doing here is I'm studying all the orbits between these two arrows that kind of go through the resonance. The arrows correspond to each other. So here you're just seeing the frequency ratio. See, there's that region in the middle where all the orbits are trapped at 1 to 1. That's just telling you what you already know. Here you're seeing the libration timescale. That's basically how fast things are going around that S&P plot for the librating orbits. You can see that these libration timescales diverge as you get to these two vertical lines. That's the separatrix, basically saying that your pendulum, when it's at exactly the separatrix, never actually oscillates. It never reaches the top. It's got an infinite period. So we're just studying kind of the dynamics of these orbits. And through this dynamics, I argue you can understand exactly what's going on in that previous picture. So first, when you get bifurcations, when you get two components that look distinctly streamlined, all you need to do in order to explain that is to paint each of the particles here based on the orbit family to which they belong. Are they a circulating or a librating particle? So here I've tried to do that. I apologize if the colors don't quite come out on the screen, but if you look at all the bifurcations that I've pulled out here, where's my pointer? Here we go. One here, one here, one here. You should notice they're all different colors from the main track that they correspond to. So I think the easiest one to see is this one right here. You've got this component down here, which is one. You've got a component up here, which is the second one. So got yet a third component over here, which is belonging to a third orbit family. A bifurcation, a distinct clustering of stars that looks like a stream, if you get a bifurcation like that, must belong to a different orbit family. Not so for these fans. These fans can all belong to the same orbit family, and yet you get this fanned out region. So what's going on there? If you paint the stars instead based on what is their libration timescale, how fast are they moving around that separatrix plot, you see the origin of these fans, which is basically the gradation here is how fast or slow is the libration timescale. You can see that wherever there's a fan, you see kind of a rainbow, you see a gradient, which is to say that every time that your particles are close enough, specifically outside the resonance, where there's this kind of long gradient in the libration time, you will get a distribution that fans out, because basically what you're getting is a bunch of particles moving around your pendulum thing at different speeds. So some of them get stuck on top for a longer time, some of them make it over the top faster, and you spread out very quickly as a result, even if all of them are circulating in this case. And so two things from here. One is that, yes, question?
What is actually the stop position in the orbital? You're saying the period diverges for a star. So does the star stop? I understand.
Good. No, the star doesn't actually stop. It's a good question. The star stops. One thing to be clear about. Let's go back to our S&P plot. Good. This is a projection into a specific choice of coordinates.
Oh, I see.
In this choice of coordinates, yes, the star stops. It stops at this point, or it never quite reaches this X point here.
That would be the slow.
A good example, if you're versed with kind of solar system or satellite dynamics, Lagrange points in where James Webb sits, the JWST sits, for example, is one of these unstable Lagrange points. And well, it actually doesn't quite sit exactly. It sits close, and it needs a lot of constant tugs to stay there. So it's not that it's stopping, and it's not like JWST is not actually stationary in the solar system. It's moving, but if you project to the right coordinate system, specifically the one that kind of relates to the rotation of the Earth around the Sun, then you get exactly these stable points.
Thank you.
Good. Back to where we were. Okay, and so yes, and I was just saying that you can see the gradation means you get a fan, versus bifurcation means you have splitting into two orbit families. So we think we understand well how the shape of the galaxy can contribute to both fanning and bifurcations. We think that also tells you pretty precisely where is the stream with respect to the resonance. You can get even more fun stuff. If you let the stream evolve enough, you get multiple bifurcations. Basically, this means multiple passages by that unstable balance point, where you can pull off additional bifurcations, spanning out, all that good stuff. You get a lot of these things for one stream. The stream has evolved for 5 decades, yes, and you get a whole bunch of components. You might say, well, some of these you will no longer be able to actually pick out from the data, and my counter is, in response to that, is yes, but it does mean that the most recent ones should still be observable. So there should always be kind of a feature. If the stream is evolving in the right place, you should be able to pick out the most recent bifurcation from this passage. Okay, to the most important question, which is, can we actually see this stuff happening? What is the likelihood of this? My initial inclination is to say it's very unlikely. But rather than try to solve this in a statistical way of kind of what is the filling factor of resonances, we just decided to take a more phenomenological approach. We know we have a catalog of streams. We have 100 or so streams observed in the Milky Way. We care about the ones that are evolving for a few orbits. We need tens of orbits to actually see resonant effects. So we take the ones that are closer into the center. We basically take a catalog of, I think, 12 or 13 streams in this case, of known streams where we think we know more or less what is their progenitor orbit on which they're evolving. What we don't know is the shape of the potential. So we look, given these orbits, at a range of potentials, or a range of dark matter halos that are squashed on an axisymmetric scale. So moving from an oblate potential that kind of conforms to the disk to a prolate potential that extends out from the disk. And we ask, given these orbits of the known streams, how many of them come close enough to resonance?
Is it actually true that we don't know the shape of our dark matter to such an extent?
We think that it should be closer to this picture because it
I would bet on that one.
I would bet on it too. And there are, I mean, right now I would say so in Q, which is the parameter of squashedness, the best constraints put it between 0.7 and 0.9. It's a pretty big range of almost spherical to quite squashed.
From what?
In terms of the density ratio between from what are the constraints from?
Yeah.
A variety of things. Some of them come actually from streams, from the orbits of streams, and kind of just trying to fit the orbit along for a typical track. Many of them are, well, the constraints themselves they're motivated by a lot of large-scale simulations that show that nearer the center, when you have baryons and dark matter.
But sorry, so you're saying you are not actually allowed to take Q greater than 1 because you say 0.7, 0.9. I
don't think that's a solved problem. I think that's where many of the papers are going. I should say some of the I mean, even if you look 10 years ago, kind of a paper that made a lot of splash in the field actually predicted a potential that looked like this, or that looked strange. It was oblate, but 90 degrees rotated with respect to the disk. That's Lomajewski, yes, which we no longer think is true necessarily, but certainly was up until.
But also the LMC falling in could actually add kind of dark matter on an odd shape.
Yes.
Yeah.
I mean, as you get further out, you expect the shape to conform less to the disk and more to the cosmic web. So, at 50 kiloparsecs, your direction of this pointing will probably be more prolate and will probably conform.
So it's not totally crazy, okay?
No, I don't think it's. I think these are all relatively reasonable choices. Now, there's nothing forcing it to be axisymmetric either. It could be tracks, or you could squash it in other ways. It doesn't even have to have any symmetry. So this is also just an approximation. But I think these are all relatively good choices. And if we were able to constrain away a few of these, that would be interesting.
You mentioned the cosmic web. Do we know anything statistically from simulations?
Well, it's great. It's a very hot topic. Planes of satellites and whatnot, if you've heard. I don't think there's a clear answer. I think there is a lot of thought around, yes, that things seem to be falling in from a certain direction. The LMC, basically, that direction seems to be preferential right now. Does that mean we know where the cosmic web is? Andromeda would also be a good guess for where matter extends, right? So catalog of streams that we know, we basically ask, given these streams, which potentials put some of these streams next to a resonance, and therefore, which stream should we look for to see, does the stream do this and therefore indicate that certain potential? Two of these streams give us very nice constraints, or I shouldn't call them constraints, but two of these streams fall in ranges where they would start ruling out certain regions of potentials. The x-axis here is that Q, this is splotchedness. And what I'm plotting on the y-axis for this green plot is the percentage of particles in a different orbit family. So this actually relates only to bifurcations. You could actually extend these regions more if we were looking also for fanning, because as I said, it can be completely circulating and still be fanning. But if you just look for a percentage of particles in a different orbit family, in a secondary orbit family, or I guess here I'm doing it in the librating orbit family. We don't want them all to be librating, so we don't highlight the central region. But all these regions where there's transitions, where some of the particles are trapped, some of the particles are not trapped, I would argue are regions where this specific stream is probing these potentials. If the potential is anywhere in this range, we should look for the stream and try to model it using the separatrix case. Same for this stream in a more prolate case. And basically, the goal would be to say, as we kind of complete our catalog of streams, as we extend this to more than just the 12 streams that we chose here as a test case, we can maybe cover more and more of this parameter space. But I would argue we're already at a not too shabby amount of parameter space, just with 2 streams covering about 15% of the total parameter space we were looking for.
And Tomer, what do you mean exactly by the green regions here? Is it that if the stream had, or if the halo had this shape, the stream would have split up, and we don't see
The
it?
stream should have split up,
Yeah.
and we should look for it. I'm not saying that we have not seen that stream split up. One of the reasons we haven't necessarily seen the stream split up is because you saw earlier kind of in the stream that's evolving, there's like I put a red circle, or I put a circle around a component that's all the way on the other side. We wouldn't necessarily think that component has anything to do with the stream. Knowing that these 2 streams are candidates means that now we can say, okay, let's look for stars in a certain region that match the kinematics, the chemistry of the stream, to say if we find 3 Ara Lyrae stars that have the same kinematics of the stream on the other side of the disk, above or below the disk, it'd be hard to explain that away as a different stream. It's not something that was below.
Well, not same kinematics, right? Because they've been moved to another orbit.
Not same kinematics, but same angular momentum, same energy, because what I've shown here doesn't affect the angular momentum and energy. So same kind of, some of the kinematic properties should be similar. Good?
How do you know the angular momentum and the energy of the stars?
If we have their 6D phase space information, which we more or
So
less
it's only taking
not
only stars that have 60 phase space.
ideally, yes, it helps. Now, to get the full picture, yes, I will argue that a lot of the things I showed here are morphological features. So it is enough to have 3 dimensions if you have a good catalog of them to say something's going on with the stream. We see streams with bifurcations. So modeling a stream that we see with a bifurcation is another way of approaching this, where you just need the morphology alone to say, okay, can I put a stream on a relatively similar orbit that gets this kind of morphology? But to identify another component, you would need full 60 phase space information.
But to make these green curves, you also need that information, right?
To make these green curves, I need more than that. I also need the potential.
Sure. Yeah.
Yes. Yes. But these green curves are kind of full knowledge, and then I'm saying, what can we rule out given these green curves? Good. So I'll just pull up my final slides. I've got a bit of time left, but I'll leave it at that. And well, I guess to conclude formally, I would argue we are at an exciting phase of studying stellar streams where we're seeing a lot of streams that deviate from the typical behavior. We learn a lot from this. It can be depressing because it complicates the picture, but we learn a lot more as a result of it. We're learning a lot about the origin of these streams, how they're evolving, the potential in which they're evolving. I'm arguing that we can also use these streams to actually see the dynamics of the Milky Way and study the shape and structure of the orientation of the Milky Way. And let us hopefully at this point, all these plots now make sense.
Okay, let's thank you. Any more questions? Yeah.
So, did you exclude Q from 120 to 126?
No, we haven't excluded anything.
Why not?
It's a good question. We should. There's nothing stopping us from.
You did not bother to look at the actual.
I did not bother to look at the actual data because this was a long paper that we wanted to use this as kind of a test case. So first, there's 2 reasons I have not done that. One is because I'm lazy and I'm not an observer. 2 is because I haven't had the time to do it yet. I will say there's a few things, and this gets back to Sarah's question earlier. That Q between those ranges sits in a regime of interest doesn't mean that this is either ruled out or proven. It means that we have to follow up and now look at the stream and say, does the stream have any features? Do we know where we need to look for additional features? Because those features might not be right next to the stream. They could be on the other side of the potential. So there's a lot of additional follow-up needed to take this information and actually make a strong claim with it. So part of the reason I guess I'm saying is, it's not just an easy kind of look for the data. If it's there, it's there. If not, it's not. You have to do some serious kind of digging to figure out exactly what are the allowed orbits, where would this stuff sit, what do you need to look for.
But it does prove that this thing is potentially durable.
That is
That
my,
would
that,
be
that was the goal of this final section of the paper and this plot, is to say, this is not just a pipe dream where, 1 out of 10,000 streams will experience it. It's actually, it probes a reasonable portion of orbits in the potential. As a theorist, I kind of like to pose that problem to the observers.
That's Sarah.
Exactly.
But I'm not an observer either at all. Okay, yeah.
How do like perturbations in the potential affect the
Excellent.
ability to see these resonances, like satellite galaxies crossing through the disk itself, maybe?
Excellent. Terrific question.
I mean, it seems like a small perturbation is enough to go from one to across the separatrix. It's
Yes.
very small, like
Terrific.
almost.
Good. So there's two regimes of interest here. It's an excellent question. It's actually a question that there may be a follow-up paper to this to deal with exactly that one, because a lot of people seem to ask that question.
Okay.
There's two regimes of interest. One is small frequent perturbations. So things like small subhalos, which maybe exist, that would push you just over the separatrix, but would do that many times. The question that you want to ask then is, how frequent are those perturbations with respect to your libration around here? If your perturbations push you across this whole diagram on a timescale that's of order your libration timescale, this resonance matters nothing, because basically everything is destroyed by this kind of random noise. My colleague Chris at the Institute has shown that for the regime of for looking at kind of perturbations of the bar, galactic bar, and perturbations in the disk, where you get a lot of these things from GMCs, from giant molecular clouds, and whatnot, all the stuff that's in the disk, that it can actually start being comparable, and you get strong effects from perturbation on your expectations from simple kind of resonant perturbation theory. So that regime is very important. For our things that we're dealing with, you're mostly in the halo. Even if you're close in, you're kind of evolving not necessarily in the disk. So the perturbations are lesser. And so generally we found that, again, this is all back of the envelope so far, there may be a paper on it in the future. Back of the envelope, we find that our libration timescale is fast enough to overcome this. At which point it becomes, yes, you still have kicks, things that push things in and push things out, but here I'd argue for everything that gets pushed in once something else gets pushed out, there's no like preference to push you in a certain direction. This is not like, it's not like an attractor in the sense that everything likes to converge to the middle.
Right.
There's no preference in the direction here. So for every for every small perturbation that pushes one star in, maybe another star gets pushed out in that case. The other regime of interest is a large perturbation. A large perturbation can push your whole stream in or your whole stream out, or even if it's a large perturbation to the potential, it can actually just move the resonance to a different location. I make a similar kind of qualitative argument there, which is for every stream that gets pushed into or out of resonance, there's an equivalent one that gets the other way around. There's no preference into getting pushed in and out. And I should say here that I've called this a resonance and I've invoked the language of kind of secular perturbation theory throughout this talk, which is not exactly accurate, because really what we care about is not the recurring motion around this separatrix plot, but really one passage by the unstable balance point. So as long as your stream has evolved such that it encounters and diverges by this unstable balance point, doesn't matter if the resonance moves away after it or if something big came and shifted it away, it's already diverged. That's an undoable divergence. So as long as you encounter this once at a certain point in the resonance is swept by, you happen to be there as the unstable balance point was there, you feel that, your stream gets diverted, your stream gets disrupted, you should see this. Maybe you're not exactly studying the potential of today. Maybe the potential has changed, but at the very least we're learning something pretty strong about our overall potential and its shape maybe a year ago in that case.
For the cases where you have, you can be pushed off or on, this sort of resonance. I mean, you showed from your video that there's actually like a physical separation between like the red and the blue streams, like those that have experienced, or on one side this separatrix and those on the other.
Mm-hmm.
But if you're kind of continually being pushed off or on, wouldn't that whole stream like just
lose coherence?
Yeah.
If there's enough heating to do that, you also would just lose coherence to the general stream. So I guess one way to counter that is to say qualitatively we see thin streams in the sky.
Yeah.
We know that there's not that kind of degree of heating
that just smears every stream away. So there's no reason it would preferentially smear away the ones that are near the separatrix.
Thank you for your question.
I have one other question, kind of related, so it's related to the middle plot that you're showing there.
Mhm.
So there has been classical streams where we have used multiple streams to model both their kinematics, morphology, to say something about the dark matter halo, right, and regain the potential shape. So now I'm just curious, do you think there could be cases where, for example, your bifurcation gets more dense than the actual stream, and we're completely guessing the orbit wrong by integrating backwards from, if we had just seen that bifurcation and try to trace it back in the potential?
You mean if we think that they're two different streams and we integrate them separately?
Yeah, or in a case where actually the bifurcation becomes denser than the stream and you actually only find the bifurcation.
And you only find the bifurcation.
I mean, some of those newer period streams.
Yeah. So first of all, that is highly possible that your bifurcation would be the densest one, especially if that's the one in the resonance, because the resonant behavior is thinner.
And could we figure that out? Is I guess the question.
You could figure it out if you were lucky and you guessed the right potential, because if you guess the right potential, the resonance will be there and everything will evolve back. It isn't to say that you are. It's a good question. If it is a resonant stream and we're evolving it in a non-resonant potential, what does that imply? You're not going to get the potential that wrong. I mean, it's not like you're going to get a completely incorrect picture if you just assume that's a stream and integrate it in a non-resonant potential orbit, because in the end, what you're seeing is a segment of an orbit, and that segment of the orbit will look similar if it's a resonant orbit in one potential and a non-resonant orbit in another. What you won't get is this ability to split one stream into two in that case. So
we maybe wouldn't go completely wrong in our potential.
You wouldn't be completely wrong. I mean, in any case, you would have to be more or less directionally correct if you're correctly modeling the shape of the stream. I think this is more interesting when you've got two streams that are suspiciously similar.
Which we have observationally.
Which we have observationally. Whereas, so if you have two streams in different parts of the sky, or but they're chemically similar. They have the same age. They have the same general. One way to explain this is, maybe it's a dwarf galaxy that fell into the collaborative cluster and all formed together, which seems to be a good way to explain Atlas Liga Uma, all of that literature. But another good way is this. In particular, you find no differences in chemistry ages.
Okay, yeah, Warren?
So what about shells, shell structures? Right, they should have the same.
You and Catherine Johnston are the same wavelength. She's been bugging me about this for 5 years. Yes, you should. So shells and shells are basically streams as well. It's just if the stream is evolving on a radial enough orbit, you spread and you look like a shell as opposed to a thin, you don't trace orbit anymore. And in theory, you should be able to get similar structures. I honestly have not thought carefully about what that looks like, because in a shell you're already spread out to a 2D plane as opposed to a 1D filament. And I haven't studied what is the resonant structure for radial orbits, although certainly there are resonances there. But it's a worthwhile question to investigate, yes.
Any other questions? Nope, let's thank you. Oh, you had a question, sorry, I couldn't tell.
Well, it's probably a dumb question.
Go for it.
I wonder about the impact of interactions or like ultralight dark matter or self-interactions.
Yet another complication that we need to take into account. So subhalos, for example, are one interaction that matters a lot, even if it's just cold dark matter. If it's ultralight dark matter, you have a lot of other substructure in the halo. To the question earlier, that does give you just kind of a constant diffusive heating term that moves things around in this picture. To the extent we know that we see stellar streams, we know that heating can't be that significant that it just kills all the streams that we see. And therefore we know that if it has an effect, it's an effect that should be quantifiable and different than this. I think the main difference I would say is, so a lot of these kind of subhalo questions, these whether it's cold dark matter, whether it's fuzzy dark matter, whether anything else that's kind of a local perturbation to the stream that punches through it.
Well, I was just thinking about the bifurcations and stuff like that kind of
Yes,
high resolution. You sort of intuitively think.
And I use the word bifurcation, and we've also used the stream community has used a bifurcation as that's what comes off when a smaller perturber hits the stream. It's a very different bifurcation, I should be clear about that. A bifurcation from, let's say, a subhalo that punches through your stream is a momentary, momentary in the galactic timescale. It's a momentary feature that is not phase mixed. It is not actually, if you look at that feature, if you look at the bifurcation, it's not actually a stream in the sense that if you let it evolve, it just phase mixes away. You've just pulled something away from the original stream track, and it looks like an arm, but after just one orbit, really, that's just going to all go away. The bifurcations we see here are actually separate streams in the sense that they are a separate clustering of particles that's moving along its own kind of orbit. In this case, one of the orbits is more or less a resonant orbit, the other one is a non-resonant orbit. So this is a global perturbation that happens to the entire stream versus a local perturbation that just kind of hits just a portion of the stream. It's another difference. A third difference is that here you will basically pull off a portion of particles versus a kind of a subhalo punching through creates a gap. You actually see where the stars should have been, and then you see an arm above. Whereas here you'll see kind of a stream, and you'll see another kind of parallel stream next to it. So there's a bunch of kind of qualitative, and you can make them quantitative differences between the local substructure effects and these global potential effects.
Right, I was not asking about local substructure. I was trying to ask if
globally, we sort of believe that fuzzy dark matter, cold dark matter. Well, actually, maybe I should turn this around. One of the things that we would want to solve for here is what is the overall shape of potential. I am not a dark matter expert in the sense that, but I believe that different dark matter models give you different predictions for what would the shape be with respect to the baryonic component.
right. No, I just meant locally whether a lot of these indicators, I'm not sure I was grasping it all that well, because in practice I don't quite see how you go about implementing these understandings to work backwards. But in any event, for a structure like that, it seems like it would get smeared out.
In the same way that any other stream would, I guess would be my argument. I mean, basically what you've got is you've got a component of stars that are evolving just like a stream because they're resonantly trapped. And that stream it could have been just a smaller stream that was born in the resonance. If that stream would have been fanned out by substructure or whatnot, there's no reason that a non-resonant stream would also not be fanned out completely. So the fact that we see thin streams in general in the galaxy means that we know that even if there are these diffusive effects, they can't be strong enough to just kill all of the kind of fine-grained structure that we see in the streams. And my only argument would be, if the substructure doesn't do that on a global sense to any stream, it wouldn't do it preferentially just to these separatrix streams because they happen to be in a resonant orbit versus a non-resonant orbit. Does that make sense?
Yeah, I guess I was thinking more the other direction. Could you put limits on things?
Yes, and that is a game that is played. That is a game that is played, that has been played well with fuzzy dark matter. It certainly, I mean, the other game that you can play is cold dark matter gives you a prediction for how many subhalos there should be at what mass scale, and you should say what is the likelihood of a stream interacting with a subhalo, and those predictions exist, and we should be finding, I think, more subhalo encounters than we necessarily see, although we're finding more and more, so maybe we're getting there. But I think a typical stream should have interacted with a large subhalo in its lifetime, based on those predictions. So yeah, there are those predictions are made. For fuzzy dark matter, the constraints are basically you constrain a certain kind of degree of how ultralight it can be, because if it's too ultralight, it fans out these streams too fast. And this has been done in several different ways, and it all seems to converge on the typical scale that we like fuzzy dark matter to be anyway, so 10 to the minus 22 or so. So it hasn't moved. This avenue has not yet moved out. Fuzzy dark matter.
Okay, let's thank Tomer. And Tomer is around for the rest of the day in 950, office 950.
We're wandering.
So how many streams do you have? You said we have a lot.
We have about 100 now.
So if you throw 100 streams at random into Q equals 0.8, will you get a single fan?
I think you should, given the fact that we just used 12 at random and we got one for it.
Those were 12 at random?
Well, that was 12. We chose 12 that exist. So I mean, it's at random in the sense that they are in the galaxy.
Oh, those were 12 innermost or something.
Yeah, well, the 12 that have the kinematics that I like.
And 2 of them for certain cues did
Encountered that.
show some.
Sure. I mean, we were looking not at just one resonance. We were looking
But
at
one
three.
thing, so bifurcation, who knows? But this fan thing, right? This should clearly be there
Yeah.
if you are anywhere close to this.
Exactly.
what you call
And you
resonance.
should easily, so, I
So
mean, the only thing,
question is, I don't believe that you didn't look at the data. You looked at the data and you saw nothing.
no, I have not looked at the data.
How can you resist? Because you showed us those pictures and
Uh,
those fans,
It's,
Well,
those
the fans are hard
fans,
to see because
we
they're low
know,
density.
so,
they're low density.
Yeah, so sometimes they could have a
So
fan.
the answer is, if you look at the existing pictures, you don't see no fans.
We do in PAL 5, there's a fan.
yeah.
So we
That-
see it in some cases, but
There's
they
a-
are
there's a
harder
few
to find,
challenges
right?
here.
Yeah.
The other thing is, I mean, the fan is easy to see if you know where the progenitor is. If you know there is a central region and there should be some symmetry.
But if
from
the data was like whatever of perfect
then
quality,
you should
you
easily
would
get
not, you
I
would
wouldn't
see
hesitate.
those fans if they were there.
Yes,
But you are saying if you look at what actually exists, you don't see fans.
We've seen
We
it
see
in a
some
few
fans.
cases.
yeah.
You see some.
I have tried, so like for example, for PAL 5, which is a stream we know that has a fan, I've certainly tried to see if that one falls by resonance. It does not.
But that
Unfortunately.
interacts with the galactic bar, and that can also.
So
be a
you are
fan.
saying fans can come from other reasons.
Yes.
That's the catch
Yes.
here. Okay. So,
Same
So
for,
we do
so,
find fans.
so here's,
observation.
let me
so
just,
fans do exist. That's
here's
good.
another
Yeah.
case that I was very excited about. Excuse this behaving slide, there we go. This one, I thought, this was one that I actually spent like 3 months looking at. So there's 2 streams here that have recently been associated. They're similar. And I was like, this is the perfect test case for a
But this
bifurcation.
doesn't look like one of your pictures.
I
does
actually made a simulation that looked very similar to this.
it? To this? Oh,
Yes.
really?
The problem is that I could never get it on an orbit close to these orbits. So again, this specific stream didn't.
So
happen
you
to
can
be on it.
produce such a thing.
But I can produce such a thing. Yes,
Not
actually,
at this location, though.
not at this location, not at this orbital, at least for the potentials that I was searching for.
Mm.
So I have certainly tried for like specific cases, but I have not done a methodical search.
And what is the current explanation of this thing?
There's actually a very
somebody
yes,
passed by.
the LMC, or I think Sagittarius passes by this one,
Torques.
and torques one of the components away. And it's a very there's actually a very nice YouTube video.
But
Which
there's
one
not-
about the one on the left or the one?
This one here.
Yeah.
So you actually see kind of, I should pull it up, but yeah, you actually see, they have a nice simulation where they run the stream and they show for a reasonable orbit of Sagittarius that comes close enough that it pulls one of the arms away.
Right, because your resonances is not the only thing which can give structure.
Exactly. So it's yet one more effect, which is why I actually think it's aptly placed in this list of a lot of things that we need to consider as we look at streams that don't just give us a simple picture.
Well, what about stars in a dwarf galaxy that are not in a streamline shape? Right, some of them are weakly bound. So if the dwarf galaxy passed by one of these separatrices, wouldn't you expect some of the stars to go one set of orbits, another set of stars?
I mean,
to go
if
another?
it's still bound,
Yeah, but like let's say close to pericenter, where most of the object is actually.
well, then if in your pericenter passage you are stripping stars, you've got a stream.
Not necessarily. That's not always true.
Well, I mean, so if you've stripped stars away from the dwarf galaxy, and they're no longer bound to the dwarf galaxy,
Yeah, but they need not form a stream if they're like warm enough.
then they
Or-
right, okay, fair. If they are so warm that they're not forming a stream, they're just kind of
Yeah.
spread out there, then you're not going to see any structures anyways. But I generally think of, I mean, that's tidal disruption. If it's tidal disruption that's cold enough, your base case is a stream or a shell. And well, I don't know the answer to shells, but in the stream case, yes, and in that case, in theory, yes, you should, whether it's a dwarf galaxy or a globular cluster. Now, I've tried this. Well, one of the first questions that people ask me is Sagittarius, which has a known bifurcation without a very good explanation. They're like, match Sagittarius. It's too hot. It's too hot. It's you can't get